Hi, everyone. So yeah, my name is Igor. I'm an SRE from Berlin, Germany. This is my first LISA. It's great to be here. I come from more of a software engineering background, so that's kind of how I got into the ops world. And so that background is probably going to influence some of my perspective on some of these things. So this is going to be a gentle and constructive rant about monitoring. And I'm going to talk about how to debug large-scale systems using events and ultimately better understanding the behavior of our production systems. So this slide is going to keep coming back. You can think of it as sort of a map for this talk, so that you can orient yourself as we talk about the individual pieces. And in the end, we're going to see how everything fits together. So with that out of the way, let's get started. Software is becoming increasingly complex. We have more machines, more services, more traffic, and more users. Let's talk about machines. This is what the cloud looks like, or a data center. It's quite a difficult environment to program for and to debug in production. And as more applications are moving to the cloud, there's a lot of opportunity to scale, but also a lot of opportunity to fail, as there are networks between all of these components. Let's talk about software. We are having to deal with increasing scales of traffic and increasing scales of engineering teams. And a common way of approaching this is through granular scale-out. In other words, service-oriented architecture. However, this greatly increases the complexity, operational complexity in particular, because we now have to manage Kubernetes clusters. We've got more services to deploy and monitor. And this also amplifies the monitoring cost, because we need to multiply the traffic by all of the services in the critical path. Let's talk about traffic. If you become successful and start getting a lot of traffic, you'll start running into the limitations of your architecture and your infrastructure pretty quickly. And events that used to be fairly rare now start happening a lot more frequently. And so it's very hard to figure out what is even going on in this kind of system. And again, more traffic is more expensive to monitor. Let's talk about users. So stability and performance problems are often specific to particular users. And very often, this happens because of skewed workloads. Because some users might be using the service a lot more heavily than others. Justin Bieber probably has more Twitter followers than you. And so a problem that affects, say, only 1% of requests, but 100% of users, might have a much higher impact than something that affects only a single user. And being able to tell the difference between those two is absolutely crucial from both an operational as well as a business standpoint. So how do we even monitor these days? We have logs and we have metrics. And we tend to think of these as separate concepts, where a log is something that looks like this, some text that's written to a log file, and a metric is something like this. So it's a bunch of numbers that we write into a time series database. And the first thing that I want to do is challenge this notion that these are somehow separate concepts, because we can actually derive metrics from the logs. And we could do this with plain old log files and run a bunch of Unix command line tools. That's usually a bit of a pain, though, because parsing these text-based formats is often kind of difficult. And also, we often don't actually have all of the information that we want in these log files. The standard Nginx logs don't even have request latency, for example. And so it can be kind of useful to put these logs into some sort of structured format, such as JSON. And so we can call these structured logs. And you don't necessarily even have to write them to a file. You could write them to, say, a Kafka topic. And it's also worth noting that this kind of text-based format will be pretty expensive for high-volume data, both in terms of CPU and in terms of bandwidth. And so it might also be worthwhile looking into some binary formats such as Avro or protobuf. So we can call these structured logs, canonical log lines, arbitrarily wide data blobs, but I like to simply call them events, where an event represents a thing that happened, such as a request or an RPC. And so we can process these events and derive metrics, where a metric then becomes an aggregation of events. But why do we even aggregate to begin with? And the reason is I don't like to scroll. Because as soon as you have more than one event per second, there's just too much stuff scrolling on the screen for you to even read it with your eyes. And also, we don't have enough pixels. So if we try to visualize the raw events, they're probably not going to fit on a single screen, even a big screen like this one. So in other words, we have too much data. And so that's why we aggregate the raw data into something that's more digestible. And we do that by using these statistical functions, such as counts and quantiles, and usually plot them as a time series. So let's talk a little bit about the kind of questions that we ask our monitoring systems. So I'm going to argue that the metrics-based monitoring systems of today are not actually well equipped to answer the kinds of questions that we need them to. And Prometheus is just one example of an entire class of monitoring systems. I would say that this applies to most monitoring systems of today. So as a motivating example, let's say we're operating a service that lets people post short messages. And now let's say that we start getting reports from users that the page is taking too long to load. Basically, it's slow. And so we might have some sort of chart that shows that there's a problem. We have tail latency that's going through the roof. And there might be some kind of alerting in place. So an alert condition that looks like this, that will send an alert if a certain percentage of requests goes over a threshold. But the only thing that this tells us is a certain number of requests was slow. It doesn't tell us anything about which ones. And being able to figure out what the common factor is between those slow events or those slow requests is absolutely essential. So for a smaller number of events, you might be able to go to the raw logs, filter out the slow ones, and then kind of look at the source data. But this very quickly becomes untenable once you have a certain number of events. And so a more effective way of doing this is usually to perform some kind of group by aggregation, and then get one distinct time series per group. And so the insight here is that most monitoring questions are actually top K type questions, which is to say, if we take the raw events, slice them by some kind of dimension, and then do a group by, and in the end, look at the largest ones, that's the kind of thing that we usually want to know. And so here's a couple examples of that. Which source IPs are sending the most traffic? Which customers are using the most resources? Which countries are experiencing the worst latency? Which hosts are exhibiting the most errors? And my favorite one to ask during any incident is, how many users are impacted and which ones? And this is so often a really difficult question to answer. And it shouldn't be. I mean, it shouldn't be this hard, right? All of these questions essentially take the form of this kind of query. But most monitoring solutions will not tell you this. And that is for one simple reason, which is cardinality. So cardinality is a fancy word for the set of possible values for a key. And generally, each value of a grouping key in a time series database needs to be stored as a separate time series. So for a system like Prometheus, you can do this with labels, where a metric has a label attached, and for each distinct value of that label, you get a separate time series. So by default, Prometheus might sum those up and kind of display it as a single line, but you can go in and look at the underlying data. So if we take this count and group by host name, we get one line per host. But Prometheus needs to store these separately, right? And so let's look at some typical cardinalities for various fields of interest. So the one that you will probably see most commonly is something like HTTP status code. And this is a fairly low cardinality field. There's not a lot of distinct status codes that you will have in your typical application, maybe tens. But what happens when you try to do this with something like user ID? Well, it kind of depends on how many users you have, but this can quickly become tens of thousands or more. And Prometheus is not designed to handle that. And it's not just user IDs. These high cardinality fields are everywhere. So look at IP addresses. We have 4 billion possible values, and over the course of a week, you might see 100K distinct source IPs. In cloud environments, machines come and go. Kubernetes pods come and go. Even host names are no longer a low cardinality field at this point. And as we deploy more frequently, the git commit hash of the software that is running in production will also change more frequently. But it actually gets worse. So going back to our event, what happens if we want to look at combinations of these fields? And so a reason why you might want to do that is either a multi-field group by or a filter in the group by, which is a very common thing to want to kind of filter down and narrow down. So we have some estimates of the cardinality for each of these fields. But if we want to filter and group by more than one of these, what actually happens is they get multiplied. So now we have 100 quintillion metrics to track. In practice, you might not get quite as big a number because the combinations need to actually exist in the source data. So it's not going to be quite as bad, but it will still get pretty big pretty quickly. And so this is a problem. So that kind of sucks. So what are we going to do about it? Well, first of all, we're going to need some events. So let's talk about how to even record those events. So events or structured logs are most useful when they contain application context. The application knows best because it has all of the information about what it's doing. And so it kind of makes sense to collect the event in the application as part of the request context, and then at the end of the request, kind of log that out in a machine-readable format. So what do you stick in such an event? So let's look at an example. So first of all, request specific information. So this is going to be pretty similar to your web server access log. But you can add some additional environment-specific stuff like the cloud region or kernel version. But where you really start to get the value out of this is once you start putting application-specific IDs and values into these events. So let's say we have a user ID. Who made this request? the version of the code that is running in production. This is especially useful during canarying. Maybe a request ID that we can use to correlate across services and databases. What about a customer plan? So there might be a free tier user that is slamming the service, and we probably want to know about it and maybe throttle them or engage them in a sales call. Feature flags. What if there's a feature that's only enabled for 1% of users? Being able to correlate that with other things like latency is a huge deal. And so the third part of the event is specific values that you might want to aggregate on. And the most common one here is probably going to be request latency, but you can look at subsections of the request. So for example, out of the time that was spent in this request, how much of that was spent on the database, on service A, service B? And this kind of cross-service latency information is often also collected as part of a distributed tracing system, so something like Zipkin or Jaeger. And these systems will produce these Gantt charts or waterfall diagrams. And we tend to think of traces and events as these separate concepts, but it turns out that we can actually derive events from traces. Because a trace is a tree that represents the execution of a single request. And this tree contains all of the information of an event and even more. So by flattening the tree and extracting the interesting bits, such as time spent on the critical path by database, service A, service B, we can construct an event from this data, from this trace data, which is ultimately a great way of analyzing traces in aggregate. And Facebook describes their system that does this called Canopy. So we have these events. We can stick them in a queue or stick them in Kafka. And so the next question then is, how do we actually query the events, and how do we do that at interactive latencies? Because when I'm in the middle of an incident, I don't want to wait 10 minutes for my Hadoop job to start. So it turns out that this is what many analytical databases already do. How do they do it? By using columnar storage. So let me talk a little bit about why columnar storage is so amazing. So if we look at the relative latencies between different operations, disk is slow, and a disk seek can take upwards of 10 milliseconds. And so if we have a 1 terabyte data set, and we try to query this data set one row at a time, then it's going to take 28 years to read all of that data. And that's because the seeks are dominating in this case. We need to do 1 seek per row. So there's an incentive to minimize seeks. And so we can do a full table scan and eliminate seeks by reading all of the data sequentially. And so now the transfer rate dominates. So we cut down from 28 years to 4 hours, which is not bad. But let's remove the slow mechanical components and try some SSDs. So now we increase the transfer rate to 1 gigabyte per second. We're down to 15 minutes for 1 terabyte. Do we really need to process 1 terabyte? I mean, most queries will probably access less than a terabyte. So we can kind of flip this question on its head and ask, what is our budget? And so if we define a latency budget, the maximum amount of time that I want to wait for a query to complete, I'm going to set that at 10 seconds. And so at 1 gigabyte per second, we can process up to 10 gigabytes per query in order to stay within this latency budget. That's 10 gigabytes per disk per concurrent query. So that's already pretty good. But this could easily become an issue if we want to query, say, 1 to 2 weeks of logs, right? Because it's still a lot of data. So how can we cram more data into those 10 gigabytes? And we can do that by using a column-oriented layout. So the key insight is that analytical queries typically only care about 2 to 3 fields. So if we have this data set that has a ton of fields, most of those queries will only want to look at very few of them. And so if we store the fields separately, say 1 file per field, we only need to read the columns that we're interested in. And this can often reduce the amount of data that needs to be accessed by 10x. In other words, we get to cram 10x more data into the 10 gigabyte budget. And so you may wonder, like, does this really make such a big difference? And the answer is yeah, it does. Like, even without any compression, we get to process 1 billion events easily. But there's more. So because the columns have the same data type, and the data is often repetitive, co-locating it can often yield much better compression. So this can often provide another 10x in savings using compression schemes like run length, dictionary, delta encoding. Now that's going to depend a lot on the data distribution and sorting keys, but suffice to say, you can get a lot out of this. And since this event data is timestamped, and queries are typically scoped to a time range, we can also partition the data by time. And so we only need to scan through the days that we're interested in. So this one's going to be a bit controversial. Probably one of the biggest cost savings that you can get is through sampling. Because even with columnar storage, event data on high traffic systems is still going to be a lot of data, especially in a service-oriented architecture. And it can be ridiculously expensive to keep all of those events. And what tends to happen is that this ends up limiting your retention window. I mean, the amount of times that I've seen these huge Elasticsearch clusters that then still only have 5 days of retention, it's kind of ridiculous, right? I mean, I don't need a full year of logs, but give me, a couple weeks worth so that I can at least compare for seasonality. Because otherwise, you have no chance of telling whether some behavior is normal and happens every Tuesday, or is a one-off event, or is something new, right? And so how does this sampling work? Well, at some point in the pipeline, you basically say, I'm going to just keep 10% of events. So this is lossy, right? But that's actually fine most of the time, especially for this kind of operational data. Because what you get out of that is the ability to have more fields, more retention, and save costs on monitoring, which is worth a lot. And also, you can be kind of smart about this, right? You don't have to throw away the rare events. You can sample the 200s heavily and then keep all of the 500s, like keep all of those rare events. And what's also kind of nice is that you can store the sample rate as part of the event so that when you're querying it, you can basically just multiply by sample rate and get an approximation of what the original count was or the original value. So now that the size has been reduced, it might actually be possible to perform more of these queries from the page cache, and we need to start thinking about, well, is CPU going to be the new bottleneck? But it turns out that columnar storage is actually also very CPU and cache friendly. The sequential access patterns enable prefetch and pipelining, and we can use SIMD instructions for efficient processing. So the same design that works well for disks is also very effective higher up in the memory hierarchy. And if all of that is still not good enough, we can still scale out some more by sharding, right? So add more disks, add more CPUs. That's always going to be an option. And then perform scatter-gather queries across all of the nodes. So by combining all of these techniques, we can fit a whole lot more information into the 10-second query budget while retaining the ability to filter and group by arbitrary high cardinality fields, which is ultimately what we want to do. This is a column store. So that's how we store and query the data. So now that we've seen all of those individual pieces, let's take a look at how they fit together. So let's revisit this map that I showed you in the beginning. So we have an application that is producing events consisting of high cardinality data. And these events are then ingested into a column store where we're able to run analytical queries interactively. The results can then be visualized as a time series. And you all, the users of the system, will be a lot more effective at your jobs. So while there are some systems that already do this, there's not really many that do it well. And so this is kind of my call to action. I really want to see more tools build on top of these ideas and give everyone the ability to perform high cardinality top K queries. And don't get me wrong, I like Prometheus. Prometheus is good, but it's not very good at this kind of thing. We need something better for debugging. We need tooling that is able to do this. So to recap, the main ideas that I want you to take away from this talk are most monitoring questions are top K questions, and monitoring systems should really optimize for that use case. We need to ask those questions about high cardinality fields, and those are a major limitation in most metrics-based monitoring systems. And finally, by capturing events and putting them in a column store, we can query high cardinality data and better understand the systems that we're operating. So if you want to read more about how some other folks have done this, I can highly recommend the Dremel and Scuba papers from Google and Facebook, respectively. Here's a bunch of references. The slides will be online, don't worry. And that's all I have. Thank you very much.